Okay.
Yeah.
So our second speaker in this morning session is Hong Chuong Doan, who is a PhD student, who was first a PhD student at Macquarie University, and now he became a postdoc. Started his postdoc just at Macquarie under supervision or guidance of Ji. And the second co-supervisor, I forgot actually, so please apologize. Hong will speak about boundedness of some singular integrals on non-doubling parabolic manifolds with ends. Please start.
Thank you, Daniel. Thank you, everyone. So the title of my talk is the boundedness of some singular integrals on non-doubling parabolic manifold with ends. So the colors of my talk is quite hot. Yeah, I use the templates of Macquarie. So my talk have for 3 sections. Firstly, I will introduce some notation used in my talk, and then I will represent my results about the functional calculus and discrete square function. So firstly, I will introduce the singular integrals. So let X be a matrix space and T is the bounded operator on L2X with an associated kernel Kxy. So we will have the singular integral T defined by the formula 1.1. And an operator T is said to be of which I want one if it satisfies the below expression for any function f in L1 and for any lambda greater than 0. And the theory of Kernel-Zygmunt theory establishes sufficient condition for operator T to be bounded on LP for P not equal to. And in this theory, there are 2 key conditions, the doubling conditions and the Hauer condition. And under those 2 conditions, operator T is of which I want 1. And if we use Maximal interpolation, T will be bounded on LP for all P greater than 1 and less than or equal to. And if the condition 1.3 is true when we swap Y1 and Y2, so we can prove that the operator T will be bounded on LP for all P greater than 2. And in many classical operators satisfies those 2 conditions, but there are still many important operators that not belong to the class of Kernel-Zygmunt theories. For example, the purely imaginary power of the Schrödinger operator on Rn. And this operator is defined by this formula where the operator L is the sum of the Laplace Beltrami operator and the non-negative potential. And the associate kernel of this operator is Kxy. And because of the effect of operator V, the kernel PTXY can be discontinuous, so the Hauer condition may fail. So to develop this theory, there are 2 main directions. The first direction is singular integral on non-homogeneous spaces. We can refer to the orders Nazarov, Strel, Wolbers, Tonsa, Hiptonans. And the other direction is singular integrals with non-smooth kernels. So there are a lot of authors have contributed to this direction. For example, Hauer, Colon, Jung, Hoffman, Maximal, Mattel, Lissinger, and others. Recently, there are a lot of authors investigates the K singular integral with non-smooth kernel on non-homogeneous spaces. So I list here some paper that I know, and these authors investigate singular integral with non-smooth kernel on non-homogeneous spaces on manifold with ends, and they mainly focus on the manifolds with the high dimension. So the topic of my thesis is focused on those manifolds, but in the lowest dimensions. And firstly, I will introduce the manifold with ends. So for a fixed integer n and an arbitrary integer m belong to the interval from 1 to n. The manifold Rm is defined by the formula 1.4, and a finite connected sum of Rm can be represented in formula 1.5, where m1 to mk belong to the interval 1 to n. And the figure 1.1 is illustrates two special cases, the manifold R1, R1, R2, and the manifold R1 and R2. And I will represent the result for the manifold R1, R2. And in the paper of Igoran, Salokov, and Ishiguro, they call it the parabolic manifold with ends. So here is some properties of this manifold. So if we denote the modulus of x is the sum of the distance from x to y, where this is the geodesic distance in M, and k is the central of M. And we can prove that the modulus of x equivalent to 1 plus the distance from x to k. And we have three properties here. And we use this property and we can check that the manifold R1, R2 is not doubling. And here is some behavior of the Higgs kernel on the manifold R1, R2. And these results come from the paper of Ioran, Ishiwata, and Salakos in 2018. And there's a lot of cases of the behavior of the Higgs kernel for the t less than or equal 1. The Higgs kernel equivalent to the Gaussian bounds. However, when x and y lie on different ends of the manifold, so this occurs some log terms in the Higgs kernel, and based on the estimates, I proved that the maximal, the highly related maximal functions on the manifold R1 and R2 is of width height 1, 1, and is bounded on LP for all 1 less than P less than infinity. And for the maximal functions M delta, where delta be the Laplace Beltrami operator on the manifold R1 and R2, I also get the same results. M delta is of width height 1, 1 and is bounded on LP for all P greater than 1 and less than infinity. And now I will investigate the behavior of Poisson semigroup kernels. And in the paper of Bùi, Dương, Lee, and Wick, they introduced the new terminologies up about of Gaussian ties. A Higgs kernel PT of the operator e raised to the power of minus TL has an upper bound of Gaussian type if PT satisfies the following expressions for some constant C and alpha, where P alpha T XY is the kernel of the Higgs semigroup E minus alpha T delta. And these definitions of upper bounds of Gaussian type includes the case of Schrodinger operators L. So that is includes all the operator that may be discontinuous. And we let case is a positive integer and denote PT case the kernel of the operator T, the square root of L raised to power case, and the exponential of minus T, the square root of L. And in the case that K is equal 0, the operator becomes the Poisson semigroup E raised to the power of minus T square root of L. And use the assumption about the upper bound of Gaussian type. I also guess that the maximal function mk square root of L is of with type 1, 1 and is bounded on LPM for all p greater than 1 and less than infinity, where m is the parabolic manifold R1, R2. And then I use this the result about the maximal function to get the estimates of the Poisson semigroup kernels. And theorem 2.3 represent the case of the Poisson semigroup kernels. So we have 3 cases. If x and y lies on the same ends of the manifold, so we have that the kernel PT case less than C on T square and multiply with this expression where K1 is the maximum of K and 1. And if x and y lie on different ends, so we have the last estimates. And use this estimates of the Poisson kernels, so I get that the holomorphic functional calculus of Laplace transform types of square root of L, m square root of L is bounded is of with type 1, 1 and bounded on LP for all p greater than 1 and less than infinity. And the results cover the purely imaginary power LIS. So these results show that we can work on with the singular integral on non-doubling spaces with non-smooth kernel. And in the last sessions, I will introduce the results about the discrete squares function. To estimate the kernels of operators, so I use the Feynman-Lindelof theorem in the lemma 3.1, and then I get the result 3.1. The kernel PZ of xy equivalent to 1 on square root of t plus 1 on t, and multiply by the exponential of this expression, and then use this kernel estimates and lemma 3.2, 3.3, 3.4, 3.5 as instrumental tools. So I get the results 3.2. So it's the main tools to get the final results about the discrete square function S delta, where S delta is defined by the formula 3.7 and the norm of S delta equivalent to the norm of the function f on LP. So that's the results of my my talk. Thank you very much for your attention. And the last one is some references I used in the talk.
Thank you, Hong. Thank you so much. Are there any questions by the audience? So now we have time for some questions. No questions? Okay. Well, we are early. So I mean,